Yep.
So Carlos put the final answer on the board here. Has everybody had a chance to check it? C1y1 plus C2y2, that's the complementary function right here. And then the second part is the particular solution. Is this the right particular solution? It is. We got 1 over...
No, that's not. It's multiplied by...
I thought we got a cosine squared on the bottom or something.
Yeah, but it's multiplied by cosine.
But it's not multiplied by y1 and...
Yeah.
Oh, no,
right.
it is right.
If you guys tell me it's right, then I'm fine.
Because y1 is cosine squared, so you simplify it.
Oh, I
Hey,
see.
no.
I see.
Y1 is
so-
cosine squared. U1 is secant squared, so that cancels
Oh,
out.
because the u1 cancels with the y1 partially.
But then it's supposed to be -1.
No.
No? Where'd they get that squared? Yeah, secant squared times cosine squared is 1.
But it's...
Let me go back.
For
y1
our
is...
u1, you got -1 over
y1 is
cosine
cosine of
squared.
3x. And u1 was, what, -1 over cosine of 3x
Cosine
squared?
squared of 3x.
That's what we got, right?
Mm-hmm.
So you multiply them together, you get negative secant of 3x. Never a doubt. Right, looks good. And then the second part was the u2, y2, and this is actually what I got also. Okay? So the answer looks good?
Mm-hmm.
And this is the particular piece right here. Okay. So we have all of these types of differential equations that we learned how to solve, right? Homogeneous, Bernoulli, linear, and separable from chapter 1. Then we learned how to do this annihilator method and variation of parameters method in chapter 6. And then we studied these linear systems in chapter 7, where we were, dealing with a coefficient matrix and trying to see if it's defective, not defective, finding eigenvalues and eigenvectors, right? So all that is great, and that's the fundamental basic material that you need to know. But the other thing I wanted to remind you about, and actually you saw it last night, is I could give you some other problem, right? That is a differential equation that is not of that type. And I could ask you still, if I give you the proper guess, remember the first problem last night? If I tell you what is the right thing to guess, then even though we haven't covered the material, you can still guess it. You plug it in and you solve for the solution that way. So I forget exactly what the problem was last night, but there is one on this review sheet as well. I may not go through the whole thing because we've just been talking about this recently, but number 11 on the review sheet is x cubed y triple prime plus x squared y double prime minus 2x y prime plus 2y equals 0. And the point is that is not a differential equation of the types we looked at before, really. I mean, it's homogeneous, but it is not a constant coefficient. There is no such thing as an auxiliary equation right now. There's no when you have an auxiliary equation, you have constant coefficients. But see, we have x's here. So obviously I cannot expect you, since we didn't cover it, I can't expect you to know how to solve that one cold, right? But if I tell you to try to find a solution of the form x to the r, in other words, I'm basically telling you how you're going to get your solution, then suddenly it's fair game, right? Then basically what you're doing is you're going to take the derivatives of y, plug them into there, and try to solve for r. In this particular case, I'll just tell you that you get the values of r are plus and minus 1 and 2. I'm going to skip a whole lot of the work and just come straight to the punchline here. You get that by plugging in for the various derivatives of x to the r in these various places here. All 4 terms will have x to the r, which can be factored out. And then what you're left with is sort of like an auxiliary equation, right? It's going to be a cubic polynomial that has 3 roots for r, and here they are. Okay? So then if you know that, well then you know that you can write down the general solution. So y of x is just c1 x to the 1 plus C2 x to the minus 1 plus C3 x to the 2. That would be the general solution. See, one reason I actually kind of like this kind of problem is that it takes the focus off of just the humdrum procedural stuff that you learn how to, do the e to the rx and find all the roots and so on. It forces you to go back and think again about the big picture of what we're doing right here. Namely, we have a third order equation. It means that the solution set, a basis for the solutions, must be three-dimensional. That was one of our theorems, right? So if I come up with 3 values of r, I can write down the solutions. On last night's exam, I don't know if you guys, I don't even remember the differential equation, but there were 2 solutions. There was the first part where I asked you to find an r value, and then the second part I asked you to find a t value. And they were both, as it turned out, 2. And so you had basically 2 solutions. In the second case, there was a natural log in it. But what I wanted people to do then was to just use the Wronskian to make sure that they are linearly independent. Or, as many people said, which was correct to say, they are not scalar multiples of each other. You could also have just said that. But these 2 functions are Li. And since the differential equation that I gave you, it was something like x squared d squared plus something. I can't remember. It was a second order equation. So you've got 2 linearly independent solutions. So then you can build the general solution for the differential equation. And then there was a part about, I gave you a particular solution, and then it's just like this. You add the complementary term to the particular term. And I gave you this part. You didn't have to do anything, really. The very last part of problem number 1 on the exam last night, you didn't have to do anything. You just basically, I think I gave you something like 1/6 of x squared, something ln of x squared, something like that. I forget what it was. I gave you that, right? You don't have to derive it. You just write that down and add it to c1 x squared plus c2 x squared ln of x. Even if you didn't get parts A, B, or C correct, you can still do the last part. Because you just write down c1 times x to the r plus c2 times x to the t ln x plus the particular solution which I gave you right here. Okay. Seems so easy now, doesn't it?
Yeah.
But anyway, I like that problem just because it was testing the big picture of chapter 6. Right? It's easy for us to get lost in the details of, I've got to find the auxiliary equation, find the roots, and then I just memorize how to write down the answer. But there's more to it than that, so I just wanted to make sure you guys are all comfortable with that. Of course, in this case of this problem, you're going to have a 3x3 Wronskian, because you've got 3 solutions, so it's a little bit more work to check linear independence, but it's not bad. It's not bad. I actually think I might have done this one on the weekend. Now that I'm looking at it again, I think over the weekend review session I probably covered that. So I think we're good. All right. Well, we've been at it for about an hour and 15 minutes, and I haven't really done a whole lot on linear algebra. So I've talked a lot about the differential equations and that sort of thing, but I think maybe it'd be good to switch gears a little bit and give you some review on sort of the middle part of the semester where we were doing differential equations and so on. Okay? Let's see. So this is kind of midterm 2, which I think we all agree is something good to review and get solid on it. So I'm going to go backwards in the notes here, and I'm going to do problem number 4 on the review sheet. Okay, so we're just jumping around. Problem number 4 says, let S equal the set of matrices of the form 2A minus B, and then B, and then negative 3B, and then 0, such that A comma B is an element of R. Okay. And what I want to have us do is show that that is a subspace of the M2 of R. Okay? So part A here, there's multiple parts, but let's show S is a subspace of M2 of R. So before we dive too far into it, do people remember checking something's a subspace? What is involved in that? So, John?
Check zero vector.
Okay, I'm going to check the zero vector is usually what I do first. Is the zero vector expressible in this form?
Yes.
If you choose, remember you get A and B are any real numbers you want. So if you choose them to be what values? Both zeros, then you get 0, 0, 0, 0, which is your zero vector. Remember, that is only a test that will be used to throw out something from being a subspace. So if the answer is no, if the zero vector is not in the set, right? Remember this fact. If the zero vector is not in the set, it's not a subspace, and we can go home, right? It's if the zero vector is in the set, then we have to proceed further. It may or may not be a subspace. We have to do more work to draw the conclusion, right? Remember this? Okay, so we've already got the zero vector is in there. Let me just write that down. Zero vector is an element of S. Check. Okay, after we've checked that, what would we do next? Let's say we've passed the zero vector test.
Closure under addition.
Closure under addition. Very good. And you can either write that as A1, which is the first axiom in the vector space definition, or sometimes I write that as CL plus. Closure under addition. And again, help me out so I can grade your papers easily by separating the parts out. Closure under addition is separate from scalar multiplication. Okay, so if I'm going to check closure under addition, how do I want to start it off? I need two vectors that are in S, right? Yeah. Okay, so how could I write that down though? Let's not use S, because S is the notation for the whole set.
R and T.
Well, what are the letters you usually use for a matrix? A and B, right? You can use R and T if you want.
I'm saying there's already A and B.
Just to spite me, I'm gonna get R and T on this final. I see it coming already. Yeah, let's use A and B. So capital A. Now, well, I could write capital A, capital B be an element of S if I want. Just say it like that. But what you really need to do, the crux of this, is to express A and B in that form up there. So what I'm going to suggest that we do is write capital A as a 2 by 2 matrix of the form that we are given. So this is going to look like 2A minus B, and then B, and then minus 3B, and then 0. Okay? It's going to look like that. And capital B is another 2 by 2 matrix. How do you want to write that one down? Make sure you use different letters here, right? You don't want to use the same ones again. So 2C minus D, and then D, negative 3D, and 0. It's all about the form. The form of the matrix. That's really the key thing that we're working with here. Okay, good. So then what do we need to do next? Oh, yeah, okay, we're good. What do we need to do next?
You need to add A and B.
Add them together. Okay, let's add them together. A plus B equals 2A minus B plus 2C minus D. That's the upper left corner. And the upper right corner is B plus D. And the lower left corner is negative 3B minus 3D. And the lower right corner is 0. So far, so good? What do we do next? John?
Factor out A plus C and B plus D.
Okay, maybe reorganize the expression so that it looks a little more like, we're trying to make sure that it looks like that form again, right? So if you, for example, look at the lower left corner for a minute. If you look at the form, it's supposed to be negative 3 times something. Well, I don't have it written that way right now. I have two terms subtracted. So what John is suggesting, I think, is that I factor out the negative 3 so that I've got the B and the D together. Okay? So let's just do that. Negative 3 times B plus D. I'm going to go ahead and simplify that bottom left entry. Of course, the bottom right, I don't have to do anything. It's just 0. upper left or upper right corner is just b plus d. Can't really do much with that. How about the upper left corner? Should I do anything with that?
First one is get the A and C together.
Put the a and the c together with a 2 out in front. Good. So 2 times a plus c. And then what? Take out a minus of b plus d. And then we ask ourselves, is that of the same form as the vectors from the set S? And the answer is yes, right? 2 times something minus something. Whatever subtracted there is what we have there. Negative 3 times that is there. Pretty good? So can I stop right there?
Well, say A plus B belongs to.
An element of S.
You definitely want to state one more thing at the end, right? The whole point of what we're doing right here, guys, is showing closure under addition. So I need to say one more thing, which is A plus B is an element of S. We really should say that. A plus B is an element of S. That's our conclusion at that point. So far, so good? Okay, what's this other thing we need to do? Scalar multiplication, right? In a vector space, we always have these 2 steps, addition and scalar multiplication. So this is axiom A2, which is also written as CL of a multiplication. Closure under scalar multiplication. How do you want to start that off? Go ahead, Grace.
Let A be as above.
Let A be as above. Very good. So we're just going to reuse the same information we wrote down before. Let A be as above. What else do we need to do?
Let K be a real number.
Good. Let K be a real number. It's a scalar. I'll just write element of R. So K is an element of R. Okay, good. So then we just need to make sure that after we take K times A, that it is an element of S again. So K times A. Of course, this is just done by scalar multiplying K through the whole matrix. So it's just K times 2A minus B, and KB, and negative 3. Well, actually, it's really K times negative 3B, and 0. Okay? So I just scalar multiplied through by K. What should we do next? Say again?
Got the K.
Rearrange it.
Rearrange it. How do you want me to rearrange this, Grace?
B, the 2 outside.
Put the 2 out in front. Good.
Parentheses, KA minus KB.
KA minus KB. All right, good. And then the upper right corner is just KB, right? And how about in the lower left corner?
Minus 3 parentheses KB.
Uh-huh. And then the lower right corner? 0. And then what do we want to say? Anything?
By default, the 2 out is going to be 2K minus 2KB.
Oh, we did something wrong. We did something wrong. Somebody want to help me with this? Help me fix this?
Minus.
It's just supposed to be, like that, right?
Yeah.
So the 2's not factored out of the whole thing. It's just factored out of the first term. Yeah, it's okay. So this, does it look better now?
Yeah.
Okay, so what do we say now?
It has the same form as us.
Yeah, but we're not going to write that all out on the paper. What do we actually
K
want to
times
say?
A is an element of S.
So K times A is an element of S. You know, if you don't show me this step, or if you don't show me like this step here, right? Then you're making my life harder because you're making me have faith that you understand that it has to be re-expressed so that it looks like this form. It's better if you write it down, then I know that you understand you have to do that. I'm not saying I would not give you credit if you just sort of put element of S here, right? It's hard for me to say you were wrong, as it really is true. But it's just better for the showing me the details that you do that extra step. Okay? When in doubt, always over-explain. Better than under-explaining. All right, there's a part B to this, which is find a basis and dimension basis and dimension for S. And does anybody have an idea how I get a basis and dimension for the set S? For
Bust
the
it out.
space? We very often find ourselves just busting out the variables that make up the set, right? If it's a null space of a matrix, we do the same thing, right? We find all of our free variables, and then we bust them out, and we have a basis for the null space. Same thing here. This is not a null space, but it's a set that has free variables in it that can be busted out. So if I bust out the vectors, so for example, if I take the matrix capital A from above, and I bust out the A, and I bust out the B, I'm going to get two specific matrices here, right? What's the first matrix going to be?
2, 0,
2, 0, 0, 0. And what's the second matrix going to be? Negative 1 and 1 and negative 3 and 0, right? Look good? All right, great. So is this my basis?
No.
That's your linear combination.
This is what's called a linear combination of the basis. But when I ask you guys for a basis, I'm actually looking for a set, right? A set. Put the squiggly braces, yeah? Put the squiggly braces there and then just write down the specific matrices. So a basis is like a list. Separated by commas, we make a list of these two 2x2 matrices. Is that clear? So what's the dimension?
2.
2, right? That's an easy one. The dimension is just the number of vectors that are in the basis. Okay? Pretty simple? Everybody good with that? Let's try another example on linear algebra. Keeping you busy here.
Oh, yes.
You're doing great. Okay, let's do number 5. Okay. Number 5 is about linear transformation. So suppose I have a transformation T. It's going to go from M2 of R, mapping it over to R squared. So I'm going to input a 2x2 matrix, and I'm going to output a vector in R2. Before I even tell you what my inputs and outputs are, I'm going to ask you a question already. Yeah, eventually, I'm going to ask you, is this thing one-to-one onto both or neither? This is like my favorite question, right? There's 4 choices there. You remember how we can always cross off 2 of them right away? Yeah, so based on just what my V and W are, my inputs and outputs, what could you tell me about this transformation already?
It's either one-to-one or onto.
I would not agree with that. John?
Oh, no, I was thinking they're onto or neither.
Okay, onto or neither?
Yes.
Final answer?
He's saying both or neither. Onto or neither? So everybody agrees neither is a possibility. Okay. You know what? Let's find the dimensions of our spaces. This is helpful always. What's the dimension of M2 of R? Remember, the dimension of the n by n matrices is always n squared, right? So 2 squared. And what's the dimension of R2? 2. So V, the inputs space, is bigger than W. These pictures sometimes help me visualize it, right? V is bigger than W, going across like that. If V is bigger than W, then can it be both? No. Which of the 2 properties is guaranteed to fail? 1-to-1 is going to fail for sure. So actually, John, you were right. It's got to be either onto or neither. It's onto or neither. Remember, by the way, 1-to-1 just means that the kernel, we're going to get into this in a minute, the kernel is trivial. And onto just means that the range is all of W. So these are the basics behind it. Okay, so now we can't really do a whole lot else until I actually give you the formula. Okay, so I have not given you a formula yet. So let me put that here. So T of A, B, C, D. Let's say I take a matrix like that. I'm going to define it to be A minus B minus 3C, comma, 2B plus D. Okay, so I'm inputting a 2 by 2 matrix, and I'm spitting out on the output a vector in R2. Okay? So before we go back to the one-to-one onto question, I just want to show that this is actually a linear transformation. I want to show that this is linear. So can I erase here in the middle? Everybody got it? See, the people watching at home can just rewind. Just scroll back and watch it again.
And pause.
Mm-hmm. And look at the solutions on the review sheet all at one time.
Yeah, exactly. It's not like this is a big secret. I was thinking I could have a little fun with this, and I could just make this, like, since I'm really into these videos now, I could make this video, it could be like 8 hours long, and like embed little answers to the final, you know, like every like, I don't know, 45 minutes, just some little thing. See how many hits I get on my website, people scrolling through, looking for all the answers. We'll probably run out of time before the final. won't be able to find everything. I guess you could pay somebody to who has 8 hours. You could pay them by the hour to sit there and record every time I say this. This is going to be on the test or something.
Wouldn't we hear it here?
Huh?
Wouldn't we hear it here?
Well, you guys will hear everything except I'm not staying for 8 hours. I've already decided that. Okay, so here we go. We're going to show that T is linear. Let's show that T is linear here. Okay, this is the first part. If you remember, to show that T is linear, what is involved in that? You sort of know the big picture of what we have to do?
That's your respect addition and scalar multiplication.
It's the two parts again, right? There's the addition and scalar multiplication. So T has to respect addition, and T has to respect scalar multiplication. So let's check those two parts. T respects addition. Okay? How do we want to start that off? I need two 2 by 2 matrices, right? And I'm going to transform their sum, right? Remember what this means really is that T of, V1 plus V2 equal T of V1 plus T of V2. This is the property that we were looking at. So in order to check that, I need two 2 by 2 matrices. So here's what I'm going to do. I'm just going to simply say we can just jump right into this here. I'm going to take my first matrix is going to be A, B, C, D, okay? And then for the second matrix, I need another matrix here. Can I call it A, B, C, D again?
No.
I shouldn't do that, right? I need different letters. X, Y, Z, W sounds pretty good to me. Okay, so we use X, Y, Z, W. Okay, now what am I going to do with this?
Transform them together.
You're going to transform them using the transformation.
Add them.
Wait a second here. We have to be very, very careful. What's the first thing we do? And the answer is not transform them.
Add them.
Add them, right? Here we're doing addition first, right? The addition is first, and then we transform. So I'm going to add them. So I'm leaving my transformation here. I'm not ready to do it yet. First, I want to add it all together. A plus X